There's a couple of problems we're going to go over now, so let's do it. So what is, and so I'm just going to review some things from pre-calc. What is an inverse function, some examples of it, and then we'll figure out how to take derivatives of inverse functions. So first, just inverse functions in general. So you got some function y equals f of x, then its inverse function, inverse function, maybe I'll call that g of x. It's some other function, and it's often abbreviated. If we started with a function named f, we would call it f with a little -1, and that doesn't mean take the reciprocal, it means inverse. So this is not reciprocal. So it's not a -1 as a power, it means invert the function. So some examples of inverse functions: if f of x is equal to, say, the square root of x, then the inverse function would be x squared, but only for x values that are greater than or equal to 0. So sometimes you have to adjust the domain of one or the other function. And it goes the other way around too. If instead we said f of x was equal to x squared, in order to invert it properly, we would have to say let x be greater than or equal to 0. And then the inverse function would be the square root of x. So this inverse thing goes back and forth. If one function is, if function A is an inverse of function B, then B is the inverse of A. Other examples you've seen before: if f of x was equal to the sine of x, that needs a domain restriction too, and the typical one is from -pi/2 to pi/2. Then we get the inverse function, which I prefer to call the arc sine, and I'll explain why in a minute, which is also sometimes called the sine inverse of x. So inverse sine or arc sine is the opposite function of the sine of x. It's another good example. If f of x was equal to e to the x, then the inverse function g of x, f inverse, would be the natural log of x. And the point of an inverse function is if you compose a function and its inverse, then you ought to get x back. They cancel each other out. And it doesn't matter the order in which they're composed, you ought to get x back. So some things about inverse functions is they reverse each other. So if f of a equals b, then f inverse of b has to equal a. In other words, if this function has the point ab, the inverse function has to have the point ba. X and y switch for an inverse function. So I'm just going to do an example of calculating an inverse function. We'll look at how the slopes of inverse functions are related, and then we'll start using that idea to come up with some new derivatives that we didn't know about before. So let's just take a kind of not too simple but not too hard example. Let's look at f of x is equal to x squared plus 2x plus 2. And if we were to graph that function, when you invert it and you switch x with y, everything that was vertical becomes horizontal. So this one opens upward. So in a positive direction for y, the inverse function would open to the right for x. And I wonder if Desmos can handle this. The inverse function should be x equals y squared. Yeah, I can handle it, plus 2x plus 2. And no, that's a lie. What did I do wrong? Oh, I'm mixing x's and y's. Y. There we go. Now, the problem is that isn't really an inverse function. A function has to be, for each input, you can only get one output. And here I can see, like, if x is 2, I get y equals 0 or y equals -2. So this blue thing ain't a function. which means to get the inverse, we would have to restrict the domain on the original function f of x and say, hey, let's just let x be greater than 1. And I know there's a way to do that here, and I forgot how, but that's okay. So I'm just going to make a note on that. For this one right here, in order to have an inverse, I have to restrict the domain x is greater than or equal to actually -1. That's what it should be. So that way I can invert it and get a function out of it. The technique for finding an inverse is one of two ways. Often the first step is to switch x and y. And then the second step is to solve for y. Sometimes people do it the other way, solve for x and then switch them. So that's an alternative way of finding it, which is pretty much the same thing. So I would rewrite this, instead of y equals, I would write it as x equals y squared plus 2y plus 2, and then I try to solve for y. So to solve for y in a situation like this, we would have to complete the square on this. So then I would take that 2 and throw it on the other side. And then what I want to do is I want to find the magic number here that completes the square, so that I focus on the 2, so that middle term b is 2. I want b over 2, which is 1, and then I want to square that, which is also 1. So this says the magic number I need here to get a perfect square is 1, so I have to add 1 on the other side too. The point of that now is that this side is a perfect square. It's the square of y plus 1. That 1 right there is this 1 right here. And that's a perfect square. On the other side, I now have x minus 1. Now I can take the square root. So I get y plus 1 square root equals x minus 1, parentheses, square root. And when we take the square root of a square, we have to do one of two things. Either we say this is the absolute value, or we throw a plus or minus on the other side. And so the typical technique is to throw a plus or minus on the other side. Now the plus or minus is a problem because that means I don't really have a function. And if we look back at Desmos, the plus is this upper part and the minus is this lower part. So I can't have both. I got to pick one or the other. And my domain restriction tells me I should pick the plus, which would be this side here to match up. So that is a problem. So I'm going to choose the plus because up above, I decided that x was going to be greater than or equal to -1. So now I just subtract the 1 to the other side. So my inverse function seems to be y equals the square root of x minus 1 outside there. So let's check to see if I got that right. And so that should be this top part of that sideways parabola. So g of x is equal to the square root of x minus 1. See that black sits right on top of that purple piece there. So that is the inverse of that right half of the parabola above. Interesting things about a function in their inverse, they will always be symmetric about the line y equals x, which is kind of cool. All right, and I guess we could demonstrate one more thing. Let's pick a point like the point, let's pick x equals 1, comma f of 1, right there. And then the other should have the reverse of that. So if I were to plot f of 1, comma 1, that should sit on the other one. And if we were to connect these 2 points here, they would make a perpendicular line to the line y equals x, which is kind of some cool geometry behind inverse functions and their related points. And that f of 1, 1 is the same point as let's see, what would that be here? 5 comma g of 5 is that same point. It's right on top. So the purple is sitting right on top of that green point. Okay. All right, so basics of inverse function, kind of review of pre-calculus there. Next thing I want to do is look at how the slopes are related for these things. So, new page. Slopes of inverse functions. Which will get us into derivatives of inverse functions. And this is the cool stuff here. Other stuff's pretty cool too, though. All right, so I'm just going to make a little graph. And then I want to show the line y equals x. Let's do that in red here. That's about right. And I'm having that there, just a reminder about a function and its inverse or symmetric about y equals x. And again, the reason is back here, because functions and its inverse switch x with y. And the only place x and y stay the same is when y is equal to x. Otherwise, there's a switch, like a to b, b to a. Wrong button. There we go. So then I'm going to make my function kind of like before. So let's say that is f of x there, kind of like I had that example. And then my inverse function, let's draw that one in blue, should look something like this. Can I do this? Something like that. Not too bad. They kind of look like mirror images. Close enough. And point of these things, if I pick some x value, then that's going to lead to a point here. And that point is going to be x comma f of x. The inverse function is going to have a related point. And so that's going to be over here and there. And that point right there can be thought about as the point f of x comma x, right? Switch x with y. So again, this blue one here, I'm going to call it g of x, and it's also the inverse of f of x. Now I can do the same thing for this point here. I can also call this point f inverse of x, comma, let's see, do I want to do that? X, sure. No. Let's see, maybe I should have named these the other way. No, I'm just going to do that for now. It's not quite right, but it's not quite wrong either. If I then, on each of these, find the slope, so let's go with a green slope for this one. Oh, geez, sorry about that. So maybe that's the slope right there. And then a blue slope for this one. Maybe that's the slope coming out of that one right there. Remember, everything that was x switches to y, and everything that was y switches to x for an inverse function. So if this green one had like a rise and a run of, say, a rise of p and a run of q, then this blue one should just switch that and have a rise of q and a run of p, because we switched everything y with x. So the change in y becomes the change in x, and the change in x becomes the change in y for an inverse function. And if you think about, like, when you're solving an equation, that's finding an inverse function. When we have a fractional multiple, to get rid of it, we multiply by the reciprocal. So I've got that f prime of x, whatever x value I pick, has the slope p over q. And then f inverse prime of x would have to be q over p, because the change in x has to switch with the change in y. is the way that has to happen with an inverse function because we switched everything x with everything y. Cool thing about multiplying reciprocals, if you multiply two reciprocals together, right, p over q times its reciprocal, q over p, you always get 1. So what that means for us is if we take f prime of x and we multiply that by f inverse prime of x, we always get 1. Next cool thing is we can solve this relationship for f inverse prime, which we could also write as the derivative with respect to x of the inverse function, kind of like that version better than this version here. Then I get 1 over the derivative of f prime of x. Now, the problem with this right here is the inverse function. If we have y equals f of x, then x has to equal f inverse of y, right? So that's part of the step of finding an inverse function. Then we switch x and y. So y is equal to f inverse of x. And so we're just going to do a little substitution in there that we're going to swap out the inverse function there. And so this is the formula for the derivative of an inverse function because of this relationship in the slopes up there and the way we solve for inverse functions. So the derivative of an inverse function is 1 divided by the derivative of the function evaluated at the inverse function. So let's test that out. We've talked about this before. We proved it with the limit of the difference quotient, that if I take the derivative with respect to x of the square root of x, then I get 1 over twice the square root of x. So I'm just going to derive that same thing. Instead of using the limit of the difference quotient, I'm going to use that inverse function theorem. So the inverse function derivative says that if you take the derivative with respect to x of some inverse function, the derivative is 1 over the original function derivative evaluated at the inverse function. So in this case, I'm going to say that f of x is equal to x squared, so that f inverse of x is the square root of x. The derivative of f of x, so f prime of x, we know is just 2x. The inverse functions theorem says to take the derivative of the inverse function, we go 1 over the derivative of the original function, and then we replace x with the inverse function. And my inverse is the square root of x. And boom, there it is. So that's just a simple example in the application of finding an inverse function. So I just wanted to show the formula works for a derivative that we already know. Now we're going to use the inverse function theorem to find some derivatives that we don't know. And this is going to get more fun. So let's stop here.